Hello and welcome. It's SFU Math 232. It's Brenda here today with section 7.3, the fundamental spaces of a matrix. So what are we going to do today? We're going to look at the way we can form different subspaces using different pieces of a matrix. So I'll give an example of this, but let's just establish what the words mean. Again, a lot of vocabulary. So the fundamental meanings are these are the basic, the important spaces of a matrix A. The row space. So we have the concept of the row space, and this is the subspace spanned by the row vectors of A. Then we have the column space of A, and we have ways of denoting these things. And then the column space of A is the space spanned by the column vectors of A. And then we also have the null space of A, which we denote this way, null of A, and that is the solution space of AX equals 0. And then we can, of course, do the same thing to the transpose of A. And because the rows and columns get interchanged on transposing, it's not surprising that the row space of the transpose is the column space of A, and the column space of the transpose of A is the row space of A. So those two things are really, you don't really get anything new. So that leads us to having these four really different subspaces: the row space, the column space, the null space, all of A, and then the null space of A transpose. So let's just look at a matrix and list out what these things are, just by way of an example. So we're going to take an m by n matrix. So I'm going to take A, m by n, where let's just make m equal to 4 and n equal to 3. Let's not make it square, just so we can get a sense of what's coming up here. So these will be rows, and these will be the number of columns, like that. Okay, so we're just going to fill it with numbers, my usual unimaginative numbers that I often pick. So we're going to have 3 columns, and then we are going to have 4 rows. Okay, so there is my 4 by 3 matrix. Of course, I can write the transpose by interchanging the rows and the columns. Okay, so there is A and A transpose. So the row space of A is the space spanned by the rows of A. What are the rows of A? 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10, 11, 12. So that is the row space, the span of those 4 vectors. The column space of A is the space spanned by the vectors that make up the columns of A. So that is 1, 4, 7, 10, 2, 5, 8, and 11, 3, 6, 9, and 12. So that is the column space. Okay, the null space is the solutions, is the space of all the solutions to AX equals 0, or for example, if we took the augmented matrix 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, we augmented it with 0, 0, 0, and we found all of the values of X. So we basically did a Gaussian elimination on this, went down to reduced row echelon form, and provided all of the solutions. That would be the null space. Okay, so you can see here, I'm going to just add it here, if I now take a look here at the columns of this guy, you can see that the columns of A transpose are the rows of A. So right here I see that this is the column space of A transpose, and then this one here is the row space of A transpose. So you can see the rows here like that. Those are these guys here. Okay, so we have that is where we're getting our um, 4 spaces. We have, let's just highlight what they are. We've got the row space of A, the column space of A. We've got the null space of A. So I didn't exactly write it like that, so let me fix that. There's the null space of A, which is the set of solutions there. And then we also have the null space of A transpose, okay, because that will be different. Because when we try to do the null space of A transpose, we are looking, this one here will be solutions to A transpose X equals 0, and then our augmented matrix will look like this: 1, 4, 7, 10, 2, 5, 8, 11, 3, 6, 9, 12, like that. Okay, and that is the null space of A transpose is not equal to the null space of A. Okay, so that gives us our 4. The boxed ones there are the 4 fundamental spaces of a matrix. All right, so another couple of words. There is a lot of vocabulary in this course. Rank and nullity. So we call the dimension of the row space the rank, and we call the dimension of the null space the nullity. Okay, and then we have 2 more ways of denoting this. There's the rank of A, and then we have the nullity of A. So let us just again concoct a matrix and then just say what these things are. So here's a matrix A. I'm going to make it very simple. You can see what's going on. So here is a matrix. There it is. If we looked at what is the row space of A is the space spanned by the row vectors. Okay, now when I'm looking at this, I can see quickly that these 3 vectors here are not linearly independent. So I could remove one of them. I'm going to remove this guy, the last guy. So I mean the row space of A is also spanned by these vectors here. Okay, so then I see that I've got 2 linearly independent vectors spanning a space. So I can see that the dimension here of the row space of A is equal to 2. There's 2 linearly independent vectors in there. And I could then, that is what I call the rank. So the rank of A is 2. Okay, then I'm going to look at what is the dimension of the null space. So for the null space, I take a look at what the solutions are to AX equals 0, and I do that by looking here at the augmented matrix and asking what are the solutions. It's already, of course, nicely in row reduced echelon form. And I see that I've got x3 is free, I've got x2 is 0, and x1 is 0. So the vectors that are in the null space look like this, where t is a real number. So I have then that the null space of A is the span of this guy. And then I have that the dimension of the null space of A is 1. There's 1 linearly independent vector in there. So then I could write that this way. Nullity of A is equal to 1. Now, you will notice that we were in working with subspaces of R3 here. We have a 3 by 3 matrix there. And you will note that the rank is 2 and the nullity is 1. And those 2 things add up to 3. That is not a coincidence. Okay, we're going to see more about this coming. Okay, so the nullity of A is the dimension of the null space. Next thing, orthogonal complements. So if we have a non-empty set of vectors in Rn, then the orthogonal complement of that set S is the set of all vectors that are orthogonal to every vector in S. So this symbol here is used to denote the orthogonal complement of S, and sometimes we call it S perp. So because of the little symbol, this guy is our symbol for perpendicular, so we can sometimes read this as S perp. And that where that perp there is short for perpendicular. Okay, so what we're saying is if we have vectors, actually this should be here, all vectors V in S. So we take every vector V in S and we try to find all the X's that are orthogonal to every single one of them. And that is what we put in the orthogonal complement of S. Okay, so let's just look at our previous example. We could ask what vectors are orthogonal to 1, 0, 0 and 0, 1, 0. So I'm saying that in this to match up with the thing here, S is the set of vectors in R3, and it's this set here. Okay, now I'm asking what is, so I'm wondering this is equal to what? So what vectors in R3 are perpendicular to both of those vectors? I want all of them. Okay, so basically I want to know, I want to find vectors, let me just call them, say, W, that are going to be in this, and they're going to look like this. They're going to look like this, A, B, C. And they are going to be such that ABC dot 1, 0, 0 will be 0, and ABC dot 0, 1, 0 will be equal to 0. So what values of A, B, and C will make this true? Well, so this one here tells me that A is going to have to be equal to 0. This one here tells me that B is going to have to be equal to 0. And then I see that there's no constraint on C. C can be anything. C can be anything. Okay, so I take those two dot products and I figured that out. So then the vectors that are in, so the W that are in this orthogonal complement are the ones that look like this, T times 0, 0, 1. Okay, so I could then write it this way, S perp, or the orthogonal complement of S, is a set of vectors, this. There they are. All of these vectors here are perpendicular to this guy and perpendicular to that guy. And it is not a coincidence either that we will notice that this orthogonal complement is exactly equal to the null space of this matrix. Okay, so there's an observation down here. The null space of A is equal to the vectors that are the orthogonal complement to the row vectors. Really master the vocabulary. Okay, if we have another set, let's take another set here. There it is. And we want to now find the orthogonal complement to that set there, S. So we want to say, what are all the vectors that are orthogonal to 0, 1, 6 and 0, 0, 2? So we want the same thing that we wanted before. We want 0, 1, 6 dot x, y, z equal to 0, and we want 0, 0, 2 dot x, y, z equals to 0. Now we can write that in on our solving linear systems way to write that. It looks like this: 0, 1, 6, 0, 0, 2, and that's going to be multiplied by x, y, z, and we want that to be equal to 0, 0. That is this system of linear equations defined here, written in the matrix format. So you can see this. I mean, this is 0 times the first row here into the column here. 0 times x plus 1 times y plus 6 times z has to equal 0. So then we can, of course, write it as the augmented matrix. And it will look like this: 0, 1, 6, 0, 0, 0, 2, 0. And then we can row reduce, which we don't really have to do much because we're pretty much already there. And we can see actually directly by looking here that x is free. So I see that x is free. I see that z is 0. And then I see that y is minus 6z. So that means that y is also 0. So I then can write out the vectors that are in this guy here. They look like this. 1, 0, 0. Okay, so the vectors in the orthogonal complement form a line through the origin parallel to this vector right here. You may see in the textbook, or you may already have experienced, that you can make this similar computation using the cross product. We are not going to be doing that. The cross product is kind of an odd beast when you think about it, okay? Because it has this sort of form where you have like I, J, K here, and then you have the vector numbers in here, 1, 2, 3, 4, 5, 6, like this, for those of you who know how to do the cross product. And then you take the determinant of this thing. It's kind of an odd thing because you've got numbers and here you've got unit vectors. I just find it kind of an odd thing, and it's not actually a standard topic in linear algebra. So we have not covered the cross product. We will not be using the cross product to answer these kind of problems. And if you're taking Math 251, you will definitely see the cross product there. Okay. There's some theorems telling us how to relate certain things to one another. So here we have, if we were to take the orthogonal complement of a subspace W and intersect, this is the intersect symbol, intersect, it with the vectors that are in W, we would end up with the set containing the 0 vector. So that's this guy right here, the set containing the 0 vector. Okay, we got another sort of complicated looking beast here. This guy here, what does this mean? This means the vector is orthogonal to every vector in the span of S. Okay, and that is the same as the orthogonal complement of S. Okay. The linear combinations gets that for you. Okay, let us just remind ourselves while we're here, what is a subspace? Okay, so that is a set of vectors, closed under multiplication and scalar multiplication. Shoot, leave myself enough space. Let's do it this way. Closed under addition, which is what I was thinking, and scalar multiplication. Okay, that's basically closed under linear combinations. Okay, so that is what is a subspace. Okay, now we've got the thing, if W is a subspace, then the complement, the orthogonal complement of the orthogonal complement gets us back to W. Okay, this is not true if this is just a subset, so caution there. Okay, in terms of being sure that these things are true, A and B are proved in the textbook. So I'm going to just refer you to that, proved in the text. And that happens to be on page 344. Okay, let's just take a look at C in R3. We're just going to have an illustration of this so we can see what's going on. Okay, so what we can do is just imagine we've got a plane. I'm going to try to draw, this is a plane in R3. Let us just draw it like this. And we can sort of imagine the axes here, for example, like that. And then here's our axes. So we've got X and Y here and Z here. So my attempt here has been to draw a plane that is parallel to the XY plane. Like that. Okay, and I'm imagining that guy to be W. Then I'm asking what vectors are in the orthogonal complement of that. So I'm thinking, okay, let me imagine every vector that is perpendicular to that plane. Okay, and that is a line. So, and that is this line right here. This line here. So I could put any sort of vector here that I want, like that. And this line, the z-axis, that is going to be the orthogonal complement of W. Okay, then I do the reverse thing. I take that line, the z-axis, as the orthogonal, well, I take it, I'm going to call it W perp, but I'm thinking of it as a line, and then I'm asking, where are all the vectors, what do all the vectors look like that are perpendicular to that line? And so I imagine something being perpendicular to this line, and for example, this vector, and then I'm sort of imagining these things going around. These are like that. So they are in effect. They are not just in effect. They are on this plane here, like that. Okay, and that gets me back to the W, like that. Okay, so when W in 3D, when W is a line, W perp is a plane, and when W is a plane, W perp is a line. Okay, here, what are we being told here? That the orthogonal complement to the set of row vectors is the same as the orthogonal complement to the span of all of the row vectors, and that is the orthogonal complement of the row space of A. The row space, the orthogonal complement of the row space is the null space, and the orthogonal complement of the null space is the row space. Okay, and then similarly, the orthogonal complement of the column space is the null space, and the orthogonal complement of the transpose of A is the column space. I'm not sure if I said transpose when I said that one. Anyways, you don't need to remember both of these because one comes from the other extremely easily. Let's just quickly note that. I could just write this one first. The orthogonal complement of the row space is equal to the null space. Okay, fine. Now what I do is I just make a substitution, A transpose for A. And I say that the row space of the orthogonal complement of the row space of A transpose is the null space of A transpose. So I basically started here with this one, and I've now made a substitution, and then I'm like, oh, what is the row space of the transpose? That is actually the column space of the original matrix. So now I'm saying that that is the orthogonal complement of that one is the orthogonal complement of this one, and then I just leave that side alone there, the null space of A transpose. And I now have started here with that guy, and I have ended up here with this guy. So I don't have to remember all of them. One comes from the other right away. Okay, so let us just talk a little bit about row equivalent matrices. When do we get row equivalent matrices? When we do Gaussian elimination. So, and when we do Gaussian elimination, we have 3 elementary row operations that we perform. That does not change the row space, those row operations. It does not change the null space. And if I row reduce a matrix and I remove the 0 vectors, then I get a basis for the row space. So let me just say a few things about this. That would be if I take some matrix A and I row reduce it to an equivalent row equivalent matrix B, I do that via elementary row operations like we always have been doing. Okay, right? Then what I'm saying, what this theorem 7.3.7 is saying, that the row space of A is equal to the row space of B. This is not changed. That space is not changed by the elementary row operations. The null space of A is equal to the null space of B. That is also unchanged. And in fact, if you think about this one. What is this telling us? I mean, if we're solving like this, AX equals 0, that would be how you would find the null space. Well, we do elementary row operations, and we get down somewhere, and we identify those as the solutions. So, and we've already been using this. Gaussian elimination does not change the solution set. That's what this is telling us, just in a different way. Okay, if we take A and we row reduce it down to B, and B is in reduced echelon form, row echelon form, then we have eliminated any linearly dependent rows. They turn to 0. Okay, they are 0. Okay, so we've eliminated the linearly independent rows there, what we do here is we choose the non-zero rows, and that is equal to a basis for the row space of A, which is equal to the row space of B. Okay, next question, or I guess a question. Do elementary row operations change the column space? And the answer to that question, stop and think about it for a sec, right? Stop the video and say to yourself, okay, there's a question here. Let me see if I can sort this out from what I know about row operations, what I know about the column space and the row space, and see if I can do that. And can I concoct an example? And then turn the video back on and see whether you were correct or whether you concocted a similar example to mine, etc. It's always better if you can come up with these things on your own, even if it takes longer, because you really own the knowledge that way. Okay, so in answer to this question, do elementary row operations change the column space? The answer to the question is yes, they do in general. Okay, let's just do this via a very simple example. Let us take a matrix A, 2 by 2 example. Here it is, 1, 0, 1, 0. Okay, so the column space of A is equal to the span of the column vectors. So that is 1, 1, that's column 1 and column 2. Now, these are not linearly independent, so I could just simplify this a little bit and say, well, that's also equal to the span of 1, 1. Okay, and then I'm going to think, what does that look like? What is the space that I can identify as the span of 1, 1? This is the line y equals x. Okay, this is all the vectors where you have scalar multiples of 1, 1. That is the line y equals x. Okay, now let's take a look at row reducing A. So I can take this guy and I can do a row operation and precisely take R2, replace it with R2 minus R1. Okay, let me call that guy B. So I've done one row operation and I've changed A into B. And now I'm going to look at the column space of B. Column space of B is equal to the span of 1, 0. The 0, 0 isn't going to get it, doesn't get us anything. Okay, so what is this? This is the line y equals 0 or the x-axis. Okay, that's clearly not the same space. This space is the line y equals x. This space is the line y equals 0. So the column space was changed via this row operation. Okay, now, what if we have a subspace and we wish to find a basis for it? So here's a subspace. We get told this is a subspace. It is a space spanned by these 1, 2, 3, 4 vectors in R5. Okay, so we've got 4 vectors. They're in R5. So the maximum possible dimension here for W is 5. So the maximum dimension for W is 4 because there's 4 vectors. I'm not sure if I said 5 or not. If I did, that was a mistake. So we've got 4 vectors. So the maximum possible dimension for W is 4, but it could be less if the vectors are not linearly independent. And I sure can't tell by looking at these vectors whether they're linearly independent or not. Okay, so the subspace, so this is how we're going to go about finding a basis here, which means we need to eliminate any linearly independent vectors. So the subspace W is the row space of this guy. So I'm going to put the vectors here. Now I'm wanting to use row space because the row space is not changed by my elementary row operations. Okay, so I don't want to do something to change this space W while I'm trying to find a basis. So I know that I can do elementary row operations on the vectors when they're rows because the row space is unchanged by elementary row operations. Okay, so I'm going to put all these guys in here. I'm basically praying, I don't know why I'm putting commas. I'm just basically praying I don't make an arithmetic mistake while doing this too. Okay, 5, 3, 1, 2, 0, minus 2, minus 7, minus 11, minus 2, 4, 6. Looks a little bit painful, I admit. Okay, so here we have the subspace W has just been recast as the row space of this matrix A. Now, I'm going to do a whole bunch of row operations, which I use the computer to do, and I'm going to make a row equivalent matrix. Here it is. Okay. So what does this tell me? The row space is the same for these two row equivalent matrices. Therefore, both both row spaces span, or both row spaces are W. What I'm saying is that these row vectors span W, and so do these row vectors span W. Okay, so I clearly don't need this guy in the end here. And it does not add anything to the program. So W then can be written in this manner as the span of the first row, the second row, the third row, and I don't need the fourth row. There it is. Okay, so now I'm guaranteed that those 3 vectors are linearly independent. and they still span. So I now have a basis. So these three vectors here are the basis vectors for W. Further, I also know that the dimension of W is 3, the number of linearly independent vectors. Okay, I knew that it couldn't be more than 4, but it turns out after this, I find that it is actually 3. Okay, now I move on to finding a basis for the orthogonal complement of W, and that is the null space of A. This is equal to the null space of A. Okay, so what I have to do is find the solution space. It's not quite as bad as it looks because a lot of the work is already done. I need to find the solution space to AX equals 0. And so I am going to want to row reduce A, which is this guy here, 2, 5, 3, 1, 2, 0, minus 2, minus 7, minus 11, minus 2, 4, 6, minus 11, 1, 6. Okay, but I've just done that. So that row reduces down to this guy here. That just column of zeros just stays there. Nothing is going to change there. And when we're doing the Gaussian elimination, there we go. Okay, now I can observe what the solution is to AX equals 0. I can look at this and I can see right away that I have two free variables, x4 and x5. So x4 is free, and I'm going to make that equal to s, and x5 is free, and I'm going to make that equal to t. Okay, then I have the three leading variables here, x1, x2, and x3. So I'm going to write out what those are in terms of s and t. x3 is equal to 7s plus 2t. X2 is minus 30s minus 8t. And x1 is 64s plus 16t. Okay, let me write that this way. x1, x2, x3, x4, x5. That is going to be s times 64 minus 30, 7, 1, 0, plus t times 16 minus 8, 2, 0, and 1. Okay, so that is 7s plus 2t minus 30s minus 8t, 64s plus 64t. I'm hoping that's correct. Okay, so that then allows me to say that the orthogonal complement of W is the span of those two vectors. There it is, minus, oh, sorry, not minus yet, 64 minus 30, 7, 1, 0, and the other guy is 16 minus 8, 2, 0, 1. Okay, and then these are the two basis vectors for the orthogonal complement of W. Okay, I can also see at this point that the dimension of W complement is 2. Okay, I could actually check. We could check a whole bunch of them. I'll show you how to check one. Feel free to check a bunch more and make sure things are working. So check. I would expect that the where am I at here? Let's not lose where I'm at. My 16. Which vector did I choose? Oh, there. I'm going to check that this vector right here, 16 minus 8, 2, 0, 1, is orthogonal to what? Okay, I just happened to pick these randomly, sort of orthogonal to this one. Okay, so but it is the case, of course, that both of these vectors here have to be orthogonal to all of the other three vectors up here. That's what it means to be an orthogonal complement. Okay, so let me just check that one. I'm checking, is this guy one of the basis vectors that is in the orthogonal complement of W, is it actually orthogonal to one of the vectors that is in W? It's a basis vector for W. Okay, and then I do that multiplication, and thank goodness it comes out to 16 minus 16, and that is 0. So yes, it is. Okay. Similarly, you could try checking the others. Okay, a couple more things by example here, things that we can do. Find conditions for B so that B is in W. So what we really are asking here is, we're given some vector B, like that, and we want to know that we want to be guaranteed that we can make it out of a linear combination of the basis vectors of W. This is what we're asking. So which vectors B1, what conditions do I have to put on B1, B2, B3, B4, and B5 to ensure that they will be able to be made out of these basis vectors? Okay, how do I do that? Well, I mean, I've got here an AX equals a B situation where, yeah, let me just write that out. I've got an AX equals B situation. So that looks like this. 1, 0, 0, minus 64, minus 16, 0, 1, 0, 38, 0, 0, 1, minus 7, minus 2, like that. B1, B2, B3, B4, B5. Okay, that is a representation of this, where you might be thinking of this C1, C2, C3. Okay, so this is sort of what we have been calling X. Maybe it would have been better if let me just change that. I'm just going to call these X1, X2, and X3. We sort of think of them as C1, C2, and C3 when we're talking about forming a linear combination, but we could be thinking of it like that. And then this looks then you can see this maybe this is AX equals B much more obviously. Okay. All right, so what I do is I row reduce this whole little guy. I'm going to ask you to check my work. I'm not going to write it out all the times that I had to do this. So I'm going to row reduce it, and I'm going to get this guy here. Luckily, you don't have to do anything to the first 3 rows. And then I can clear these ones to 0, and I end up with this, B1, B2, B3. And here I end up with B4 plus 64B1 minus 30B2 plus 7B3. And then I end up here B5 plus 16B1 minus 8B2 plus 2B3, like that. Okay, now I want this system to be consistent. Otherwise, I mean, I cannot find values of x1, x2, and x3 if the system is not consistent. And you can see that these things here are all 0. That means that these two guys have to be 0 for consistency. Okay, so that's telling me that B1 and B2 and B3 can be anything I want. Anything. And then I have to have that these two entries here in this column on the far right must be 0. That tells me that B4 will have to be equal to minus 64B1 plus 30B2 minus 7B3, and that B5 will have to be equal to minus 16B1 plus 8B2 minus 2B3. Okay. So what you could do now, in fact, if you wanted to, is you could use this constraint, the conditions for B. You could form one vector B that is in W and one vector B that is not in W using these conditions here. Then you could check using Gaussian elimination, perhaps doing that on a computer so you don't have to do it by hand, whether you're, if indeed that is the case. Okay, that would probably be actually quite a good exercise to make sure that you understand what's happened here. Okay, so now what I want to do is find a homogeneous linear system whose solution space is W. Let us remind ourselves what W is. W is the space that is the span of these three vectors here, 1, 0, 0, minus 64, minus 16, 0, 1, 0, 38, and 0, 0, 1, minus 7, minus 2. Okay, that is what W is. The basis vectors for the orthogonal complement of W are these guys here, minus 64, minus 30, 7, 1, 0, and this guy, 16, minus 8, 2, 0, and 1. Okay, now I want to find B, Bx equals 0. So the solution space is W. So what do I claim here? I'm basically saying, what matrix is this? And I'm claiming that matrix B is in fact the basis vectors for the orthogonal complement as rows. This guy. Yeah? Because the row space of B is the orthogonal complement of W. So the null space, which is the solution to Bx equals 0, is W comp, the orthogonal complement of W, and I take the orthogonal complement of it, and that is W. Therefore, the linear system is this. Minus 64x1 minus 30x2 plus 7x3 plus x4 is equal to 0, and 16x1 minus 8x2 plus 2x3 plus x5 is equal to 0. Okay. A lot to take in. This last example, I think, fairly difficult conceptually when you first see these sort of things. So spend some time, perhaps after watching the lecture, go back and start again with this last question and see whether you can understand when to use the rows, when to use the columns, when to make something equivalent to a row space, and when to make it equivalent to a column space. Okay, so it is a bit easy, I think, sometimes to start to solve a problem and then accidentally enter the vectors in rows when they should be in the columns, or accidentally enter them as columns when they should be in the rows. Okay. All right. I will be back with section 7.4 shortly. Thank you.